limits in the 1D case, the limit of f of x as x approaches a is equal to L if, for any epsilon greater than 0, no matter how small, there's some value delta, also positive, so that for any x, where for all x that are within this distance of a, the distance between f of x and this limit L is less than epsilon. Then we can make f of x as close as we want, so arbitrarily close, by making x close enough to a. Intuitively, that's what this definition is trying to say in terms of delta and epsilon. Now, one thing that's very important to point out about limits is this right here. Notice that we only consider x are close to a, but not equal to a. The reason for that is, so limits are about behavior of function near a point, not at x equals a. For instance, if we have a situation where we have a function, we see what's going on near x equals a, it's behaving like this, but at x equals a, value is not what we might expect from a graph. Instead, the value is here. So this is a point, x is a, and y is f of a. So f of a is, for whatever reason, defined to be this. That this value is the limit as x approaches a. What's actually happening at a is completely irrelevant for the purpose of defining what a limit is. It's only what's happening as you approach. But when the behavior of a function near a point coincides with a value at the point, what you have is a very important concept of continuity. Function continuous if you can graph it without taking your pencil off the paper, which is a nice intuitive working definition. What continuity really means is that if you take the limit as you approach a point of your function, behavior near a coincides with behavior at a, that's when you have continuity. So these are the main ideas behind limits and continuity. They're brought back from 167 from a single variable case. Now we're going to be talking about distance between vectors. The distance between points. So in the one-dimensional case, single variable case, just the absolute value. So the distance between x minus y is just x and y is just the absolute value of x minus y. In the multi-dimensional case, it's the magnitude of a difference of vectors. So the distance between x and y, these are two vectors that belong to some n-dimensional space. So for most part, it'll be R2 or R3, so it's 2D or 3D. You can use this notation for it. So we have the double bar indicating the magnitude of a vector. The vector in question is just x minus y. And if y have these components, x1, x2, up to xn, y1, y2, up to yn, then the distance between these vectors is going to be square root of sum of squares. We're just going to look at corresponding components, take their difference, add up all of these squares and take the square root, which is entirely consistent with what's going on here. The absolute value can be defined to be square root of x minus y squared. Now one thing that's kind of unfortunate, this notation, a double bar, that magnitude of a vector, some books, including Stewart, just use the single bar, but this is what I'm used to, so this is what I'll be using on the board. Track corresponding components, take the sum of squares of the components of that vector represents their difference. So this is our measure of size that we need in order to talk about limits in a multi-dimensional. So suppose now we have a function f that takes in n variables and outputs m variables. So it could be a vector valued function. We're not proposing any restrictions on how many inputs or outputs f takes. Then you can say that the limit as x, which is now a vector quantity, approaches a, also a vector quantity, f of x, which also could be a vector. Everything here could be a vector. It's equal to some vector b if we choose any epsilon greater than 0, again, no matter how small, there exists some delta, also positive, so that if the magnitude of this vector, x minus a, is less than delta, and again, the vector x is not equal to a, it's just very close to it, but the difference between these vectors, f of x minus b, is less than epsilon. So it's exactly the same as the one-dimensional definition, only instead of absolute value, it's using the magnitude of a vector. Now, let's take a look at an example of this, how we can use this definition. Because we're working in even 2 dimensions, the picture gets a bit more complicated when it comes to computing limits, because you have more directions in which to travel. In one-dimensional case, you're trying to compute the limit of a function as you approach a certain point. You can see what happens as x approaches a from the left or from the right. Those are your only 2 options. What if it's something like this? Function approaching a different value from the right as opposed to the left. The limit, it doesn't exist. You may have one-sided limits. DNE does not exist, but you may have a limit from the left or the limit from the right with the superscript, a minus and a plus mean. Now what about multivariable? Well, here's your point. A, somewhere in the xy plane. So you want the behavior of a function as x and y approach this point. Well, you can approach it from infinitely many directions. So you have to make sure that no matter what direction x and y are approaching a from, that the value that is approached is the same. Otherwise, the limit doesn't exist. This is really convenient to check them all, and that's why you actually end up appealing to this definition to see if the limit exists or not. Function of 2 variables, x and y, over square root of x squared plus y squared, and we want the limit as x and y approach 0, 0. So what we do is we assume that epsilon is positive, and we check, can we find delta such that the difference between fxy and the limit is less than epsilon? And here it's absolute value because we're just taking a difference of numbers again. F takes in two variables, but it only puts out one. Whenever the magnitude of this vector, which is just going to be the square root of x squared plus y squared, so it's the difference between the vector xy and the vector 0, 0, is less than delta. Well, first of all, we need at least a candidate for the limiting value. So what you can do to get an idea as to what the limit might be, of course you can try plugging in x and y equals 0, but what happens if we do? Yeah, divided by 0, you actually get 0 over 0, which is an indeterminate form. So one thing you could do is you can try setting x equals 0, y non-zero, then you let y approach 0. So this is a way of letting x, y go to 0, 0, along one particular path. Or you can do the opposite. You can set y equals 0 and then let x approach 0 and see what happens. Here's another path that's useful. Set x equal y and let x and y go to 0 together. If we try any of these, what appears to be the limit? If you set x or y equal to 0 but leave the other non-zero, you're gonna get 0 over something non-zero. So there's no division by 0 problem here. And one of these suggests that the limit b is actually equal to 0. The only question is there a possibility that we might be, if we approach 0, 0 along some other path, that we might get a different value, or maybe no value at all? Well, we can't simply check all of them. There are infinitely many. So instead, we'll appeal to the definition. We'll fill in b equals 0 and see if we can actually prove that everything works out. So we'll assume that our limit is 0. So given epsilon, can we find delta so that f of x minus 0, so that would be xy over square root of x squared plus y squared, is less than epsilon, whenever this distance, which is x squared plus y squared, square root, is less than delta. So boil it down to, if we have some epsilon, can we find a delta that makes all this work? The way you answer that question is try to find an upper bound on this quantity, the difference between the function value and your limit. Try to find an upper bound on that in terms of the distance between x's. So try to bound the distance in y's in terms of the distance between x's. So more concretely, try to find an upper bound for this in terms of this. Because then it'll give you a way to actually come up with a formula for delta in terms of epsilon. That's how you can get everything to work out, because you have some epsilon you don't know or care what it is. But for any epsilon you choose, you got to be able to find some delta that makes this work. And that's where this finding an upper bound comes into play. And that's what I'll show you now. So let's start manipulating this right here. Y over square root of x squared plus y squared. So what I'm going to do is I'm going to break up this product, pull out the x, then we have everything else. But I can rewrite that as, here we have the absolute value of y. So really what we have is the square root of y squared. You can write it that way. What's the largest this can be? No matter what x and y are, how big can it possibly get? 1's the largest that it can possibly get. If x is equal to 0, this whole thing is 1. It's never going to get bigger than 1 because this denominator is always going to be at least as large as the numerator.